Our main motivation is the ability to outsource or delegate computations to some powerful external server or say just the cloud. So we're some weak computational device such as a smartphone or a tablet, and we want to outsource our computation to the cloud. So the picture is this one. We have our weak laptop. It wants to perform some computational task, for example, to compute the value of a function. So it interacts with the cloud and gets whatever the result is. However, our laptop is a little bit suspicious, so it's afraid that either the cloud is making a mistake or is even being intentionally deceitful. So in addition to the actual result, our laptop wants some proof that the result is correct, and it wants to be able to verify this proof very efficiently. In particular, this verification should be much more efficient than just performing the computation by yourself. In this talk, I want to focus on what's called a one-round argument system. So one round is kind of straightforward. So we just want one message sent from our laptop to the cloud, which includes some input x and maybe some additional information. It gets back an answer, which is the result f of x, together with a proof, and decides whether whether to accept this value of f of x or not. Okay, that's a one-round. That's a one-round thing. And by an argument system, what I mean is that it's not a proof system in the sense that we don't care if there are very inefficient ways to convince the verifier of something wrong. We only care about sort of computationally bounded malicious clouds. And let's be a little bit more formal, put it on a formal framework. So the framework is somewhat similar to that of an interactive proof. So we have a prover P and a verifier V. And the prover is trying to convince the verifier to accept a statement of the form x belongs to a language L. So they interact. We'd like the interaction to be sort of minimal. And we require sort of the usual notion of completeness. So for every true statement, every x that belongs to L, the verifier is going to accept with high probability. We only require computational soundness. So for any false statement, x that does not belong to L, no matter what a cheating prover do, as long as it's polynomial time, it won't convince the verifier to accept with negligible probability. And we want efficiency. So we want our V to be very efficient. In particular, we want it to be more efficient than the time t, where t is the time that it takes to just directly compute L. Okay, so we want the running time of V to be fast. And we also want the running time of the prover to be relatively efficient. So proving should not be much more harder than computing. So we want time polynomial and t. Okay, so that's the efficiency that we want. And before telling you what our results are, let me mention some prior work that has been done on this problem. So if you allow 4 messages, so just sort of 2 rounds of interaction, Kilian, about 20 years ago, showed such a really beautiful protocol for any language in NP. Again, this is based on collision-resistant hashing. The verifier is very efficient, and it's a really neat protocol. But it has 4 messages. If you actually want to minimize this interaction and get to a 2-message,
what do you mean for all of NP? You said that
so when we're talking about NP, I let the prover also get a witness, if that's what's troubling you. Okay. But in this talk, I'm actually going to focus on languages in P. So, so if we go down to a one-round argument system, then by combining the work of Goldwasser, Kalai, and Guy Rothblum together with the work of Kalai and Raz, you can obtain such a delegation protocol for any language that can be computed in sort of bounded depth. Again, this is based on sub-exponentially secure private information retrieval. If you don't know what that is, then just it's a plausible cryptographic assumption. Not so important. And C. But sort of the running time is going to depend on the depth. Okay, let me just briefly mention a few other works. So in the random oracle model, we have a beautiful result of Silvio Micali, which is just sort of a one message, but it's in the random oracle model. If you allow a pre-processing step, which means that before the parties, the verifier sees the input X, it's allowed to do sort of an expensive pre-processing step. We also have a lot of work in that model. There's also a lot of beautiful works in that sort of obtain very strong results, but under what's known as non-falsifiable assumptions, which are sort of controversial, I guess, cryptographic assumptions, such as knowledge of exponent. And let me just mention that these non-falsifiable assumptions are in some sense necessary for NP, and I won't get into any details of that. Okay, so let me tell you what our main results, or a couple of variants of our main result, are. So Again, we're going to assume sub-exponentially hard PIR. We're going to get to that later, so just forget about that for now. What we get is a delegation scheme for any language in P. So suppose you have a language that you can compute in n cubed time, or n to the 5 time, where the verifier is going to run almost in linear time. So this O tilde is hiding polylog factors. And the prover is going to be polynomial time. The communication is polylogarithmic in n. Okay? Different variant of that. So if you only want to assume a slightly weaker cryptographic assumption, so only quasi-polynomial security, you actually get the same result, except that the communication increases to n to the epsilon. And actually, I want to point out what the exact dependency between the parameters are. So the most general theorem says that for every language that you can compute in time t, you obtain a delegation protocol where the verifier works in time n times polylog t, plus poly k, where k is a security parameter, and the prover runs in time polynomial in tn and k. So that's kind of the general statement. Okay, and I want to tell you a little bit about how we achieve this. And our starting point is a protocol suggested by Aiello, Bat, Ostrowski, and Uzgopolan, who suggested a very natural way to combine a multi-prover interactive proof system together with a fully homomorphic encryption scheme to obtain a delegation protocol. Okay, and I want to start off by quickly reminding you what these two objects are, an MIP and an FHE. And actually, instead of an FHE, you can put private information retrieval, but it's going to be easier for me to describe it using FHE. Okay, so what is an MIP, a multi-prover interactive proof system? This is a very natural extension of the standard notion of an interactive proof system. It was suggested by Benor, Goldwasser, Kilian, and Wigderson. And the idea is to extend the single prover interactive proof system by having many provers who only interact with a verifier. They only talk with a verifier, not among themselves. Okay, so we have these L provers. They only talk directly to the verifier. And we have the standard completeness and soundness condition, where completeness here is information theoretical. We're not putting a bound on the cheating provers. Okay, just the standard notion of an MIP. And of course, we have this seminal result of Babai, Fortnow, and Lund, which says that this class MIP equals NXP. So that's MIP. Fully homomorphic encryption, I assume you're familiar with it, so let me just very briefly remind you. So the idea is just a public key encryption scheme in which, in addition to the key generation, encryption, and decryption algorithms, you have an additional algorithm called an evaluation algorithm that gets as input ciphertext, which is an encryption of some message M, and a circuit C. And without knowing the decryption key, it manages to produce an encryption of C of M. Okay, so it's somehow evaluating C underneath encryption. So that's a fully homomorphic encryption scheme. For purposes of this talk, you can think of the output as being a fresh encryption of CFM. It's not important for our results. Good. So what was the suggestion of Aiello? Let me just remind you, the idea is to take an MIP together with an FHE to obtain a delegation protocol. So we start off with an MIP protocol. We have our verifier and we have our L provers. And the first thing that I want to do is encrypt each one of the queries. So just a one-round MIP, you send your queries, you get back answers. The first thing that I want to do is have the verifier encrypt its L queries. Now the provers seem to be, they have a problem. They're getting encrypted queries, but they can actually do whatever they did before and evaluate that homomorphically and do that sort of answer the queries underneath encryption. Okay, so they answer back, they get encrypted queries, they send back encrypted answers. A crucial point here is that each one of these L queries is encrypted under a different key. Okay, so that's the first step. The second step says, well, we have our L provers. Let's just bunch them all together into a single prover. Okay, so we take these L encrypted queries. We just send it to one prover. That prover is supposed to homomorphically evaluate the L provers from before on these ciphertexts. Okay, so that's a suggestion. The intuition is that because each one of these queries is encrypted under a different encryption key, then when you answer one query, you can't actually use the other queries because they're encrypted under a different key. So that's the intuition here. But unfortunately, Dwork, Lamberg, Naor, Nissim, and Reingold showed that this intuition is sort of, in some sense, false. Okay, so that doesn't quite work. Later on, Kala and Raz showed that it is correct if what you start off with is not an MIP, but rather a single prover interactive proof system. What we show is a generalization of Kala and Raz's result, which shows that this protocol works if the underlying MIP satisfies a stronger notion of soundness. And this stronger notion is called no signaling soundness. And I'm going to describe that in depth. Okay, so if we start off with a no signaling MIP and we add an FHE, we do get a delegation protocol. Okay, so what is this no signaling soundness? So the idea is, in the standard MIP setting, the provers don't talk at all. I want to allow them a very minimal form of communication. Of course, I can't let them talk in full generality because that will just sort of collapse down to a single prover interactive proof system. And the way that I restrict the communication is to say that the answer of each one of the provers, it may depend as a function on queries that the other provers got, but not as a random variable. If you look at its distribution, then that distribution is independent in the probabilistic sense from the other queries. Okay, and I want to talk about that a little bit more formally. So in full generality, when we have an MIP, I want to consider a general prover strategy. It just says for every sequence of L queries, what is the distribution of the L answers? That's a sort of a very general prover strategy. If you're talking about a standard MIP, then this prover strategy actually needs to be a product distribution because each answer only depends on that specific query. In the no signaling setting, the idea is as follows. So take any two sequences of queries, and suppose that they agree on some subset of the query on some subset. Then the distribution of answers on that subset needs to be identically distributed in the two cases. Or in other words, if you just take a single sequence of queries, the answers on a subset of the queries are independent of the other queries in the probabilistic sense. Okay, we're going to see an example of that. Right. Right. Yeah. Yeah. In the one I explained it with two. Yeah. Yeah. Okay. So what is a no signaling MIP? Basically, an MIP that is resistant to these kind of stronger attacks. Okay. So an MIP in which any no signaling prover strategy can convince the verifier to accept false statements, except with some small probability. So I guess going back to this protocol of Aiello et al., you have your encrypted queries, and you want to say that each encrypted query can't be used in order to answer one of the other queries. But if you look at semantic security, then what it will guarantee to you that it can't affect the distribution of the answer, but potentially maybe it can be used as a function. I'm not sure if that was, but I'm going to show an example which I think will.
Why do you call it no signaling?
So we'll get to that in 2 slides, I think. So, okay, so let's see an example of the power of a no signaling strategy. So I want to show a very simple MIP, and I'll show a no signaling attack that breaks it, that breaks the sounds. So the idea is that we have our verifier, we have 2 provers. The verifier just sends 2 queries to the 2 provers. Each one of the provers just answers with some answer. And what the verifier does is it just checks whether the XOR of the 2 answers is equal to some predicate of X in the queries. Okay, kind of a simple protocol. So how would a no signaling attack on this protocol look like? So consider the following attack. So the first prover is just going to answer with a uniform random bit, A1. The second prover takes this random bit, A1, and XORs it with the value of the predicate. Okay, so first thing that you can see is that if you XOR these 2 results, then the verifier sees what it wants to see and will accept. Okay, so this works, but why is this no signaling? So if you actually fix the 2 queries, and you look at the first answer, A1, it's just a uniform bit. Also, if you forget about A1 and you look only on A2, it's also just a uniform bit. Okay, so each one of these answers individually is uniform. Of course, their joint distribution is very not uniform, but each one of them by themselves is uniform. So that in particular, that means that it's no signaling. Okay? And let me just point out that this example isn't contrived. So there are actually some very fundamental PCP or MIP verifiers that work this way. They just XOR the answers. Okay, so this kind of attack will break their soundness. And let me go back to Avishai's question. So it turns out that this concept has a relation to quantum MIP, where quantum MIP, I'm really not an expert about quantum, so I'll only mention it very briefly. So in a quantum MIP, the idea is that the cheating provers are allowed to share an entangled quantum state. Okay, and it turns out that these entangled strategies are in particular no signaling. Okay, and this term no signaling came from the quantum world. And basically the idea is that sort of one set of queries cannot signal to the other set of queries. That's answering. But it comes from Einstein, or it's like very old stuff. And one nice property, which is, I think is one of the reasons that people are interested in this no signaling soundness, is that even if sort of quantum theory changes in some way, as long as this principle that information cannot travel faster than light remains valid, then no signaling soundness will still capture these new sort of quantum strategies. That's just a nice feature. Okay, so let me tell you a little bit about what's known about these no signaling MIPs. So let's define this class MIP-NS as a class of languages that have no signaling MIP protocols where the verifier runs in polynomial time. Sort of the natural extension of the class MIP. And you can think of a scaled down version as well, but let's put that aside for a second. So it was known that this class of no signaling MIP contains p-space and is contained in exp. And just recall that the class MIP, the standard class MIP, we know that it's equal to n-exp. So that this means that this no signaling power that we give to the cheating provers is gaining them a lot, right? We know that we're already limited to exp. And in particular, all the known PCP and MIPs that are designed for an exp are broken by no signaling strategies, just because of the fact that this class is contained in exp. Another thing that I wanted to point out is that it was known that this class, when you restrict it to just two provers, so two MIP with no signaling soundness, was known to be equal to p-space. Okay? What we show is that if you allow more provers than just two, this class actually equals to exp. And the scaled down version of it is equal to p, which is what we will use for our delegation protocol. We'll see in the next slide. But for exp, polynomial. So this is our main technical result, which says that, so suppose we have a language L that you can compute in time t, then we construct an MIP with no signaling soundness, where the verifier runs in time n times polylog t, and the prover runs in time poly t. The number of provers is polylogarithmic in t, so if we're talking about t that is exp, then we'll get to a polynomial, and also the communication is polylog t. So the scaled up version will just tell you that this MIP NS is equal to exp. The scaled down version, by scaled down I mean that we're looking at languages in p, then t is going to be a polynomial, and then our MIP verifier runs in n times polylog n time, and the prover is polynomial time. Yes, sorry. And throughout this talk is the size of the inputs. Yeah. Yeah. Right. Right. The cryptographic result, it won't improve it very fundamentally because we're squishing all the provers together anyhow. So we didn't try to. No. Only in terms of the no signaling result, but in terms of the cryptographic result, you could try to minimize the communication, but so either the provers or the amount of communication with each prover. But it's not the bottleneck, I guess. But I know that people who are interested in no signaling MIPs by themselves are interested in the number of provers. Okay, so sort of as I hinted so far, our proof has two main steps. The first one is completely information theoretic. So we construct an efficient, no signaling MIP protocol for every language in P, or the scale-up version for any language in exp. And that's completely information theoretic. There are no cryptographic assumptions here. The second step, which is a cryptographic step, applies a general transformation, taking any no signaling MIP, in particular the one that we just constructed, together with a private information retrieval scheme to obtain a delegation protocol. Okay, so these are the two main steps. I wanted, because I'm limited on time, I wanted to tell you a little bit more about the first step in this talk. Okay? And it's a little bit complicated, so this will be kind of a high-level overview, but I hope it will give you an idea of what's going on. Okay, so remember we have a language L. We want to construct a no-signaling MIP for L. And for this high-level overview, so I want to think of L as being, you can compute L in time t, simultaneously in time t and in space S. And for this talk, I want to make the simplifying assumption that S is at most linear. Okay, so we can compute it in polynomial time and linear space. And we want to construct a no-signaling MIP for this language L. And to do that, we're going to use a well-known PCP, specifically the BFLS PCP of Babai, Fortnow, Levin, and Szegedy. The actual details of the PCP won't be important for the talk. They're very important for the construction. Okay, so how does the protocol work? We're trying to construct this MIP. Let's start with the provers. So each one of the provers, first of all, generates the entire tableau of the computation. What do I mean by that tableau? So we have this table. It has, its depth is t, and its width is s. You can think of every layer as being the entire state, or I'm not sure what it's called, of the Turing machine. The entire sort of storage tape and configuration, exactly, of the Turing machine. So we have our configurations of the Turing machine, and sort of we start off with the input. That's what we have in our tape, and every layer is just sort of one move of the Turing machine. Okay, that's a tableau of the computation. So I want to think of every layer as being computed by and or NOT gates applied to the previous layer. Okay, so that's a standard notion. What I want to do, is to take this computation and to encode it via PCP. So before we just had a table, the PCP adds sort of, I think of it as another dimension. Okay, so instead of a table, now we have a cube. But the table from before is still sort of, still exists inside this cube. Okay, and the actual details of the PCP aren't crucial at this point. Okay, so each one of these provers expects to be queried on a single point of the PCP, and the honest provers just answer whatever they see in the PCP. Okay, that's what they do. So that's the provers. Let's move on to the verifier. The verifier is also very similar to the BFLS verifier. In particular, the first thing that it does is to generate the BFLS queries. It's going to randomly permute the queries and kind of send each one of the queries after being shuffled together to each one of the provers. And actually, in addition to the queries of the BFLS verifier, I'm going to also add to these shuffled queries explicitly checks about the input and output gates. Okay, and also permute all of these guys together and send them to the provers. The provers answer, the honest provers answer with the points on the PCP, and our verifier accepts if the PCP verifier accepts and the input and output gates are correct. So the input gates are supposed to be X, which the verifier just has explicitly, and the output gate, of course, needs to be 1, right? Because the provers are trying to convince us to accept. So that's the... No, so I'm kind of finding, so it's going to read the output gate, and I'm going to define the notion of reading next. Okay, but sort of in some sense, it explicitly checks the output gate. Okay, so completeness is kind of obvious. It just follows directly from the completeness of the BFLS PCP. So let's talk about soundness. And of course, we want to show soundness against no signaling cheating strategies. And let me just mention a few of the challenges that we encounter when proving no signaling soundness. So the first thing, sort of just by definition, is that each one of the answers may depend as a function on queries that other provers got, which is something that doesn't happen in the classical setting. Okay, but that's sort of just by definition. A couple of other things that I want to point out. So a major problem is that for these no signaling MIPs, we don't have what's known as a low degree test, which is sort of at the core of the BFLS or many other PCP constructions. In particular, we can't just assume that cheating provers are answering according to some low degree polynomial. And this is a huge problem. Another problem that we have is that there's no known parallel repetition for no signaling MIPs. It actually is known for 2 prover no signaling MIPs. This is due to Hollenstein, but for 3 or more provers, it's not known. Lastly, another sort of headache that we have is that these cheating prover strategies are going to be randomized. In the classical setting, they could be randomized, but you can very easily just fix the randomness. So now we really have to deal with the fact that they're randomized. Okay, so let me try to give a high-level overview of how we do prove that no signaling soundness works. So let's assume that we have a cheating, no signaling proof strategy. So we have these cheating provers, P1 star up to PL star, that manage to convince the verifier to accept a false statement with very high probability. Okay, to prove the actual theorem, we need to show that they can't even do it with low probability. For purposes of this talk, I want to assume that these cheating provers convince the verifier with very, very high probability to accept. And I want to derive a contradiction. But what I want to point out is that once we fix these prover strategies, then sort of their answers as distributions or as random variables are defined. And now I can ask these provers, given this bunch of queries, what are your answers? And it's defined, right? We fixed our provers. They need to tell me what the distribution is. And I can even ask them queries that the verifier would never ask. I still need to have some distribution as an answer. And we're going to use this to derive a contradiction. Okay?
Because there are no signaling there to answer, if we were signaling, simply...
They could do right. So if you're in the classical, I mean, if they could do anything, then if you give them queries that are not distributed according to the verifier's distribution, they could say, forget about it, I'm not answering. Right. Right. So now if I ask, even if just one query is distributed according to what the verifier would ask, then no matter what the other queries are, the distribution of the answer needs to be correct. Yeah. I mean, this is the property of being a no signaling. Essentially, yes. I mean, this is sort of you just said what a no signaling property is. Yeah, that's what we use.
Can you actually, in a sense, weaken the no signaling property for the proof to go through? It seems, in a sense, weaken the no signaling.
Oh, so maybe I misunderstood you.
You need to answer like no signaling uniformity. They should answer any crazy question as well as the.
But in what sense? As well, in what sense?
As a pair column, pair prover question is valid.
So first of all, I needed to hold not just for any single prover, but also for sets of provers. And that's just, unless I misunderstood you, it's just saying exactly what no signaling means. Okay, so just going back. So we assume that we have this cheating strategy and we want to derive a contradiction. And I want to introduce this notion of reading the point in the PCP. Okay, and you can think of it abstractly, but I want to make it a little bit more concrete. So reading a point in the PCP means taking a random line that goes through this point. The line is supposed to be sort of three-dimensional, but it was hard for me to do. So you take this random line, and you're going to ask each one of the provers one of the points on the line. You get back answers. You view the answers as lying on a low-degree polynomial. You interpolate that polynomial, and you look at the value at the red point, and that's reading the value of a point. Okay, the actual details are not important, but what I want to stress is that we have some notion of reading the value of a given point in the PCP. Okay, but I didn't say sort of any result yet. What I want to show you is a lemma that uses this notion of reading. So let's fix some gate in the computation. So we have some transition between two layers. We have, say, some AND gate. So the output is some value x, which is computed as the AND of the two inputs, y and z. This technical lemma that I just mentioned says that we can read the value of a gate by just taking random lines through the input and output gate values. So if we take these random lines and do this interpolation, the three values that we get are going to be with very high probability. They're going to be consistent. What do I mean by consistent? Just that the output value is sort of the value of the gate computed on the two input values. So in the case of an AND, the output should be an AND of the two inputs. But just very sort of local consistency. So that's all this lemma is saying, is that we can sort of, in our proof, we can obtain some sort of local consistency from the prover's answers. And the proof of this lemma uses some sort of algebraic PCP-like techniques, and I won't have time to get into it, but if you're interested, then please come and ask me. Okay, but we have this notion of reading the value of a gate in a consistent way. So how are we going to use that? Okay, so let's try a first attempt, which, as you can guess, won't work, but let's try. So the idea is to simultaneously just read all of the values in the tableau. Okay? So we know that for each individual gate, and here we're using the no signaling property, we know that for each individual gate, when we ask about it, with probability 1 minus epsilon, we're going to get a consistent value for each one of the gates. So when we ask about all of the gates, just by taking the union bound, we get that with probability 1 minus t times s, which is just the size of the tableau, times epsilon. And I'm thinking of epsilon as being very small, so much smaller than 1 over t times s. We get sort of global consistency. So the entire table is consistent. Now, since we explicitly checked the input and output gates, that means that the entire computation is the correct computation on the input x. And therefore, the output bit should be a 0, and we explicitly checked that it's a 1. So the verifier is supposed to reject in this case. So we derive the contradiction. Okay, so that sounds convincing. But the major problem is that we want to query all of the points in the tableau. So we need t times s provers to do that. Right? So we wanted to query much more than t points. For that, we needed these t times s, at least t times s provers. If we have that many provers, then sort of our running time is going to be t times s, and of course, just getting running time t is kind of easy, just because the language can be computed in time t. So it's not that this doesn't work; it's just that the efficiency isn't good. Okay. So let's try something else. So let's look at some gate that sort of is a computation just of the second layer as a function of the first layer. Okay, so we fix this gate. And let's take these random lines and read the value of the gate. So first of all, we know that the inputs are correct with probability 1 minus delta, just because we sort of explicitly check that the inputs are correct. We also know that the value of each individual gate is consistent with probability 1 minus epsilon. Okay? Therefore, if I just take a union bound, I know that, so if they're both consistent and correct, it means that the output needs to be correct with probability 1 minus epsilon minus delta. Now, a cool feature of this no signaling property is that what happens now if I only ask about the point in the second layer? We know that when I asked about other points, the value that I got was correct with some probability. The no signaling property tells me that if I ask about this point, and no matter what I ask about other points, the value should still have the same distribution. And in particular, it should still be correct with the same probability. With respect to the input x. The input x is fixed. Yeah. Okay?
Oh, it's just because you're in the second level now. The x was fixed, right?
Yeah, so I'm going to go and keep fixing as I go up. Okay, but the first layer is fixed to x, and I check this explicitly. So here I'm in the second layer. I know that this guy over here is going to be correct with probability 1 minus epsilon minus delta. And I can make the same argument about its neighbor, right? So now let's see what happens when I ask about these two guys and sort of some gate that computes on them. So we know that each one of these guys by itself is correct with probability 1 minus epsilon minus delta. So now I can take a union bound over both and know that with probability 1 minus 2 epsilon minus 2 delta, both are going to be correct. I also know that this gate, because of our lemma, I know that its value is going to be consistent with probability 1 minus epsilon. So what I get is that this guy in the third layer needs to be correct with probability 1 minus 3 epsilon minus 2 delta. Okay? And you can actually keep on doing proceeding like this, but unfortunately your error grows exponentially in the depth. So this would be great if our computation can be done in low depth, and in particular it just already gives a delegation protocol that works for low depth computation. But this was already known, as I mentioned in the beginning. Okay, so let's try to get a new result and do something else. So our third attempt, and here the idea is going to be to use I only need to like 3, right? No, but I need to ask about these gates, so the three points. I need, but I mean, if in my proof I'm going to ask 3 queries, then I need there to be 3 provers, And actually, each one of through each point, I'm taking a random line, so I need a little bit more than 3. But not a lot of provers at all. In this third attempt, I'm actually going to use, I want to use order S provers where S is the width of the table. Okay, so many more provers, but recall that we assumed that S is linear, so not that many. And the idea is as follows. So let's try to read the entire first and second layers of the computation, okay, through this notion of reading through random lines. We know that the entire lower layer is correct with probability 1 minus delta. That's because we explicitly checked this. We know that each one of the gates in the second layer is consistent with probability 1 minus epsilon. So just taking a union bound over this entire second layer, we get that with probability 1 minus s times epsilon, this entire second layer is consistent. Okay, so just taking a union bound over these two events, we see that the entire second layer is correct with probability 1 minus s times epsilon minus delta. Good. Now we can ask what happens when instead of asking the first and second layer, I ask about the second and third layer. So if I look at the second layer, we know from before that the answer was supposed to be correct with this probability. By the no signaling property, we know that even if I ask about the third layer instead of the first layer, this probability needs to stay the same. Okay, so when I read the entire second layer, I'm supposed to get the correct answers with probability 1 minus s times epsilon minus delta. As for the third layer, as before, I know that it's going to be consistent with probability 1 minus s times epsilon. So taking a union bound over these two events, we get that the third layer is correct with probability 1 minus 2s epsilon minus this delta. Okay, we can keep on doing this argument, going up and up. What we'll get is that the top layer is correct with probability 1 minus t times s times epsilon. T is, remember, the height of the table.
So you're doing a union bound over the pairs of rows?
Yeah, but each time over just a pair, not over the entire tableau. And again, our epsilon and delta are sufficiently small so that this event actually, this top layer is going to be correct with high probability. If it's correct, it means that, in particular, the output bit is correct. So we start off with x that does not belong to L, so the output bit needs to be a 0. And we explicitly check that it's a 1. So the verifier in this case should also reject. Okay, so this third attempt actually works. So what we have is that the number of provers there is essentially 2 times s for the two layers. It's more than that because through each point we need to take a random line. So the running time becomes roughly order s. Okay, it's actually a little bit more. And this gives delegation for any language that you can compute in polynomial time and linear space. And let me just point out that we have a construction that works also for larger space, superlinear space, any polynomial. So for any polynomial time computation, but that construction is a little bit more complicated. I won't have time to describe it, but if you're interested, then please come and ask me. Okay, so that was the proof that I wanted to show. Let me just briefly mention a few of the missing details. So the first thing is just this construction for larger S. We also assume that provers cheat with very high probability, with probability 99, even more than 99%. And to prove our theorem, we need to show that even provers that cheat with 1% can't work. And this is a problem because there's no parallel repetition now. So this causes us a bit of a headache. We also need to exactly formalize what this notion of reading means and to prove the lemma, which is some technical work, and a few other details that I didn't mention. So let me just summarize. What I showed today was a delegation scheme, or our results are a delegation scheme, a cryptographic delegation scheme for any language in P, where the verifier runs in quasi-linear time. And actually, in a new result, we managed to get this time down to exactly linear, but pay in a few other parameters. And the prover is polynomial time, and this is assuming private information retrieval. And we have an information theoretic result, which says that this class MIP MS is equal to exp. So that's it. Thank you. Yes. Yeah.
Is it just for subsets of size 1? Or
Um,
do you use larger
so,
subsets?
so there are actually lines hiding going through every point.
Oh.
So that would cost you. Yeah. So I hid that. But
You didn't mention too much the time of the prover. I mean, you said it's polynomial.
so the time of the prover is essentially computing the tableau of the computation. That's polynomial time, and then encoding using the PCP. That's what the prover, the honest provers essentially do. And encoding using the constructing a PCP of a computation is polynomial in T.
Well, I can't do it right now in my head. I don't know
Okay.
if it does, but did you make efforts to make this time slow?
To decrease the polynomial, no.
Yeah. I mean,
No, it's interesting, I think. But we didn't try to optimize the neither the polynomial nor, we have polylog T. We didn't try to optimize this polylog factors. So I think it's interesting.
Why did you start with BFLS 91? Was it just because the construction with the loaded readbusiness makes it?
Essentially because it's sort of the question was why did we start with the BFLS PCP? So I guess that sort of it had one property that we liked in it is that sort of there's a notion of the correct value. Once you fix your input x, there's a notion of the correct value at every point in the PCP. Even if x is in L, it belongs to the language or it doesn't belong. So essentially and also it's simpler than other more complicated PCPs. So we tried a lot. We put a lot of effort into trying to make it work, and then it did.
I also had another question. Are there cases where you could imagine in practice the no signaling assumption holds?
Sorry?
But besides the quantum motivation, when might we see in the real world cases where the provers do communicate, but the extent of their cheating is limited?
So first of all, there's this quantum setting.
Right.
Other than the quantum setting, I think that sort of it's just motivated by the fact that if you send encryptions of queries, then the type, what I didn't show, but we show in the paper, is that the type of attacks that you can do are essentially these, or potentially could do, we don't know that you can actually do them, are no signaling attacks. Okay, if you get encrypted queries encrypted under different keys, then sort of this kind of corresponds to the no signaling setting.
Thanks, one again.